The topic we're gonna talk about today is surface properties. Firstly, we are going to talk about interfacial phenomena. Interfacial phenomena occurs at the interface or boundary surface between a suspended particle and the continuous phase material. Hence, it is always associated with dispersed systems. Dispersed phase is a mixture of two substances, a dispersed phase and a continuous phase. The particles can be in any of these phases and in the form of solid, liquid, or gas. Dispersed systems also can exist in any one of 9 different combinations of the particle phase and the continuous phase. As you can see in this table, these are the examples of cases where interfaces are formed. In this video, we are going to focus more on the liquid-liquid interfaces, which are milk and butter, as well as the gas-liquid interfaces, which are whipped egg whites. In a dispersed system, the two phases cannot be soluble or miscible with each other. They must be immiscible. This means that they must not dissolve in each other to form a solution. As you can see, if we mix any oil in a glass of water, the oil will not dissolve in water. Instead, the oil will separate into smaller droplets that remain suspended and visible in the continuous phase, which is water. In this type of system, an interface exists between the surface of each droplet, which is the dispersed phase, and the surrounding liquid, which is the continuous phase, in contact with the particle's surface. However, in examples such as salt or sugar crystals dissolved in a glass of water is not a dispersed system. It is a true solution as the crystals will disappear. This is the formation of single-phase systems, even though there are two different substances being mixed together. When they do not have two separate phases, no interface is formed, and hence, no interfacial phenomena can happen. Interfacial phenomena can affect the physical properties of materials. When interfaces are adsorbed by bipolar molecules, such as surfactants and emulsifiers, the behavior of this two-phase material to which they are added can be totally changed. For example, in mayonnaise, when an emulsifier like lecithin is added to the oil and water dispersed system, a permanent miscible emulsion is formed. An emulsion is a colloidal system in which a liquid is dispersed as droplets in another liquid, which it is immiscible. The stability of emulsions is determined by the viscosity of the continuous phase, the presence and concentration of emulsifier, the size of the droplets, as well as the ratio of dispersed phase to the continuous phase. There are two types of emulsions that we will discuss in this video: oil-in-water emulsion, which is mayonnaise and milk, and water-in-oil emulsion, which is butter. As you can see, this is the ingredient list of mayonnaise. Mayonnaise contains egg yolks. Egg yolks has lecithin, which is an emulsifier. Hence, it can form a stable emulsion. The next ingredient list is butter. Butter forms a stable emulsion due to the presence of lecithin, which is soy lecithin, in the ingredient list, and hence it does not separate upon storage. Emulsifiers are important as it ensures the food texture, prevents separation, as well as ensure the food quality does not become undesirable upon storage. What about milk? Milk does not contain added emulsifiers, but it does not separate upon storage. Milk is also an emulsion with fat particles dispersed in an aqueous watery environment, but it does not need additional emulsifiers. This is due to the physico-chemical properties of oil-in-water emulsions that are stabilized by milk proteins such as casein, which acts as an emulsifier in milk emulsion. There are a few challenges encountered in emulsion stability. For example, breaking. Due to coalescence and creaming combined, the oil separates completely from water so that it floats at the top in a single continuous layer, as you can see in the diagram. How do we better disperse system food product? In particle size wise, homogenization, especially in milk, can increase the surface area. This can be done by high shearing and vigorous mixing. The increase in surface area by decreasing the particle size can increase the area of interfacial contact and hence making it more stable. Why is emulsification important? A consumer's decision to purchase one food brand over the other is largely based on its consistency, taste, and appearance. With correct processing method, it provides a smoother texture for the food product and hence making the food quality better. Emulsification can also increase a food stability. For example, the intensive pressure applied by high-pressure homogenizer can cause a food to attain more stable chemical structures, and this allows for a longer period of freshness. This works by preventing or delaying creaming of the fat and increasing light reflection as the total surface area of fat globule is increased.
So now, let's talk about foams. Foam is a colloidal dispersion in which gas is a dispersed phase and liquid is the continuous phase. Foam is considered as a modified liquid and it can contribute to volume and texture. The addition of solids such as emulsifier can help stabilize foams. One of the food examples related to foaming is egg white, and whipping of egg white is being discussed. During the whipping process, air comes into the solution to form bubbles. The hydrophobic regions in the protein facilitate the absorption at the interface, then partial unfolding of the protein, which is known as surface denaturation. This change in the molecular configuration results in the loss of solubility or precipitation of some proteins, which collect at the liquid-air interface. The reduction in surface tension facilitates the forming of new interfaces and more bubbles. Egg albumin present in foods such as meringues and angel cake has excellent foaming properties. The structure of egg albumin, which consists of composite mixtures of proteins, allows it to perform well in foams because each component carries out a different function. The properties are determined by the ability to adsorb on the air-liquid interface rapidly during whipping or bubbling, and by its ability to form a cohesive viscoelastic film by way of intermolecular interactions. Do you know that around 30% of the eggs produced are processed in the egg industry? Three most well-known uses of eggs are based on that. Liquid eggs coagulate or solidify when heated, and the examples are cakes, breads, and crackers. The second use of eggs include whipping of egg white produces lighter and airier products, and the food examples include meringues and angel cake. The third most well-known use of eggs in the food industry include emulsifying egg yolk phospholipids and lipoproteins to produce mayonnaise, salad dressing, and sauces. The stability of foam is one of the challenges to face in food industries. Stability of foam is achieved by the association of the partially unfolded molecules during whipping process, forming a stabilizing film around the bubbles. Excessive whipping of the protein solution produces a higher concentration of smaller bubbles, resulting in more unstable foams. This instability of foam depends on the decrease in the bubble elasticity. It results from excessive insolubilization of proteins at the air albumin interface. When the egg white foam is unstable or has been overly beaten, it will produce a volumeless, lumpy, coarse and grainy appearance. Foams collapse by three principal mechanisms. One of them is bubble disproportionation as a function of time. The bubbles reduce in size with time due to air diffusion from the interior, which is a region of higher pressure. The second one is lamellar rupture. Bubbles coalesce quickly due to pushing and pulling forces causing hose formation between two bubbles. Finally, drainage. Water around the bubbles naturally drains down to the liquid layer, removing proteins from the foam around the bubble, which eventually becomes too thin to support the bubble. As you can see, this is the difference between a perfect meringue and a filled meringue which has collapsed. So now, the question is, how can we overcome this? There are a few ways to modify the properties. These include controlling the beating time to avoid overbeating. The foam volume increases as a function of the beating time. Egg albumen forms unstable, dry foams after prolonged whipping, which can result in a drained material of poor whipping quality. The addition of sugar into egg white causes a delay of foam formation, especially in the first part of the beating period. The inhibition effect on the whipping properties is caused by the addition of sucrose, lactose, dextrose, and maltose. Despite the inhibition effect, the delay of foam formation helps prevent overbeating. Foaming is essentially important for related food products with respect to shelf life and appearance of the product, and must be maintained when subject to process variations such as heating, mixing, and cutting. The product's appearance and textural properties can be influenced by the size distribution of air bubbles in foam. Foams with a uniform distribution of small air bubbles imparts body, smoothness, and lightness to a food. Uniform distribution of fine air cells in the structure of foods is contributed by the protein in foams. Body and smoothness of food foams is associated with the formation of air bubbles that allow volatilization of flavors with enhanced palatability of the food. Formation of foams requires low surface tension so that air can be fully incorporated while in the liquid. With respect to this, we can now look more into surface tension. Surface tension is the forces involved in interfacial tension. Surface tension explains the complex situations occurring at the interface between the surfaces of both phases in the cases of solid gas and liquid gas interfaces. Have you ever realized that if you put a paper clip onto water, it will actually float although paper clip is denser than water? Well, this is due to the tendency of the surface of water to behave like a stretched elastic membrane. The molecules at the interfaces have a higher energy level than those in the interior of the material. Water has a strong surface tension because the cohesive property of water gives it a high surface tension. This explains why the paperclip and small insects can float on water. Water has the properties of adhesion and cohesion. Adhesion is the attraction of molecules of different substances. For example, water molecules can stick to other things, and this can be seen when water molecules adhere to leaves, forming water droplets. Cohesion is the attraction between molecules of the same substance. It holds hydrogen bonds together to create surface tension on water. Examples of cohesion include teardrop, raindrop, and drop of water coming from the faucet. The cohesive forces enable the water drop to form foam around it. Work input is needed to alter this condition, such as in making foams or emulsions.